Hi guys! In this lesson, I will explain the working principle of transformers, which we can see in many electrical devices that we use in our daily life and in power plants without going into their types. Transformers are one of the electrical machines that do not have any moving parts, which are used to reduce or increase the voltage and current level of any alternating current without changing its frequency. Transformers from the power sources in our desktop computers into the chargers of laptops, phones, or many electronic devices, from the power supplies that need to reduce the AC and convert it to DC, to transfer stations at the output of power plants in much larger structures, at city entrances, and in some neighborhoods. It is possible to see that it is used in many devices and places, from voltage reduction and distribution centers. Transformers transfer energy from one circuit to another with the principle of electromagnetic induction. In this way, power is transferred from one circuit to another more efficiently. Until the voltage produced in the power plants comes to our homes as 110 volts AC, it is first exposed to the step-up and then to the step-down process with transformers. First of all, a voltage is produced in the power plant with the help of generators. Then, this voltage is converted to high voltage with the help of transformers. Then, this high voltage is carried to the city entrances with transfer stations and big poles. High voltage is reduced with the help of transformers at the city entrances. Eventually, it reaches our homes as 110 volts AC. Here, you may have a question why the electricity produced in the power plant is increased and then reduced again. I can explain this as follows. During the transport of electric current to long distances, the AC voltage produced in the power plants is increased and transported as high voltage to the cities in order to reduce the losses through heat in the wires. So, how do we reduce losses in this way? The formula for power is found by P equals V times I. If we increase the voltage value in this formula, the current value will decrease. Because the power produced in an ideal electrical system is equal to the consumed power, the power value is constant. Since the current decreases here, there will be less heating in the wires. Thus, the losses are reduced. Now let's see how a transformer works. In order to better understand the working logic of the transformer, we must first look at Ampere's law. According to this law, a magnetic field is formed around a conductor through which a certain current is flowing. When we wrap this conductor on the core, which is made of a ferromagnetic material such as iron with a very good magnetic permeability, we increase the intensity of the magnetic field. In fact, it is an electromagnet in a coil structure. Here, this electromagnet has north and south poles according to the direction of the current. While the current flowing through the conductor and the direction of the magnetic field are constant if it is direct current, the intensity and direction of the magnetic field is constantly changing if it is alternating current. When we wind these two electromagnet coils on an iron core and place them close to each other, a transformer is formed. Here, the AC voltage at the input creates a variable magnetic field on the coil windings. This magnetic field transforms into magnetic flux on the iron core. The magnetic flux in this core creates an AC voltage on the coil at the output, again with the effect of the variable magnetic field. Thus, the input voltage is converted wirelessly by magnetic induction principle. So, why do we need to transfer voltage in this way? In fact, what is done here is to adjust the intensity of the tension. The intensity of the voltage will change according to the number of windings at the input and output. With transformers, only an AC voltage is increased and decreased, friends. Because the direction and intensity of the AC at the entrance changes at any moment depending on time, the direction and intensity of the magnetic field it creates changes at every moment. When this field cuts the output windings, an AC voltage is induced in the windings. A DC voltage cannot be stepped up or down. Because when DC is applied to the input windings of the transformers, a magnetic field is formed again. However, this magnetic field is a constant field. Since the direction and intensity of this field will not change, there is no voltage induction in the output windings. In a transformer circuit, it is basically represented by the symbol you see here. The input part is called primary, and the output part is called secondary. Here, we see that the winding at the primary input of the transformer is too much, and the winding at the secondary output is less. This transformer is a step-down transformer. It will convert the high voltage at the input to a lower voltage at the output. This transformer is a step-up transformer. We see that the primary winding is less than the secondary winding. It will convert the low voltage at its input to a higher voltage at its output. As we can see here, the step-up and step-down process in the transformer is according to the number of windings at the input and output. So, how do we show them as formulas? Now, let's take a look at it. The conversion ratio in the transformer is expressed by the lowercase n. This ratio is the ratio of the number of turns. Here, if we call the primary voltage Vp, the number of primary windings Np, and the secondary voltage Vs, and the secondary winding Ns. If we consider the transformer as an ideal transformer without any loss, the ratio of the primary winding to the secondary winding is equal to the ratio of the primary voltage to the secondary voltage. From here, we can see that the number of windings is directly proportional to the voltage value. At the same time, this ratio will be equal to the ratio of the secondary current to the primary current. In other words, the voltage values and the current value are inversely proportional. The iron core, which is used to ensure the passage of magnetic flux inside the transformer, is not as a single piece of casting as you can see here, but consists of very thin plates stacked on top of each other and glued together. The reason for doing it this way is to reduce energy losses. As such, the efficiency can reach over 90%. In very large transformers used in power plants, overheating will occur, as lowering or boosting processes are carried out at high voltages. In order to dissipate this heat, oil is passed through it and cooling is provided. Therefore, such transformers have an oil tank. This tank is used to store the oil used for the cooling process. In addition, this oil also provides insulation inside the transformer. This is the basic structure and working logic of the transformer. I hope it was helpful and you liked it. Hope to see you in the next lesson. Goodbye!